All right. Hello and welcome to lesson 2.3. We're talking acceleration today. Now, we've already gone over velocity, which is how quickly something is moving, but acceleration kind of takes that a step further. Acceleration is how quickly you change your velocity, and you've probably actually seen statistics regarding acceleration before. In terms of cars. Now cars, they measure their velocity in miles per hour, and any old car can reach a speed of 100 miles per hour. Any modern car can do so, but the impressive thing for a fast car is really how quickly they can get to that speed. So let me show you some statistics that will feel kind of familiar. Most of you have seen the 0 to 60 statistic. Now, like I said, a Toyota Corolla, which is a very affordable car, can reach 60 miles per hour, and so can a very expensive Ferrari. But the impressive thing about the Ferrari is that it can reach a velocity of 60 miles per hour in a very short time, and we can see that here with the numbers. A Toyota Corolla, if you slam on the gas, it'll take you 8 seconds to go from a resting position all the way up to a velocity of 60 miles per hour. A Ferrari, on the other hand, can go from a rest position to a top speed, to a speed of 60 in just 2.4 seconds. So this is a representation of acceleration. They're both getting to a speed of 60, and they could both go faster than that. But what this represents is the rate at which it's speeding up. To reiterate, the Ferrari has a better acceleration because it gets to that 60 in a much shorter time. That's a much more impressive time. So let's put a definition on this. Let's actually do a calculation in order to better understand what acceleration is. So here's our definition in words. In words, acceleration is the rate at which velocity changes. The equation for that is A equals delta V over T. We're going to spice it up a little bit. Technically, A should have a little arrow above it, and so should V. But if those are confusing to you, you can just leave them out. The meaning of the arrows is that we need to keep track of positives and negatives. So if acceleration points west, it's negative. If velocity points west, it's negative. And those arrows are there as a reminder of that fact. Let's go to units. Of course, time is going to be measured in seconds, as usual. Velocity, well, change in velocity is what this actually means. The triangle means change. That's measured in meters per second. And acceleration has sort of a cool unit. We can see it showing itself here. This is meters per second. This is seconds. So this is meters per second per second. Another way to write it, meters per second squared. All right, there's a lot to unpack in this equation. Namely, here, what we can do with the delta V and the unit of meters per second per second. take a quick look at this. You probably don't need to write it down, but just answer the question. If a car goes from 40 meters per second to 47 meters per second, what is its change in velocity? Most of you can do that without even using a calculator, and you just go like this, 47 minus 40. And so our change is 7. We've increased our velocity by 7. That's pretty important to notice, because anytime we have a delta, this feature appears. It shows itself. So delta V, a change in velocity, can also be represented like this, Vf minus Vo. So that's sort of a mini equation that we can apply to anything. Like, we could say this for delta. I mean, it doesn't matter what the letter is. Like, I'm just going to make up a variable, delta F. Let's say delta P. We have used delta P before. Would be P final minus P initial. So this pattern kind of shows itself a lot. Whenever you see a delta, you can do final minus initial with that value. So let's jot that in here. It'll be useful later on. Delta V equals V final minus V initial. Now we'll probably come back to this, but the meaning of this unit, meters per second, is your velocity is changing by blank meters per second every second. For example, maybe you have an acceleration of 10 meters per second. You're going to gain 10 meters per second of speed every second. Or if your acceleration is negative 8 meters per second, you're going to lose 8 meters per second of speed, velocity, every second. So let's take these ideas and apply them to an actual situation we can picture. Okay. Here we go. Starting from rest. A plane accelerates down a runway. Calculate the acceleration of the plane if it achieves a velocity of 70 meters per second after 29 seconds of motion. I'll read that back to you. Starting from rest, a plane accelerates down a runway. Calculate the acceleration of the plane if it achieves a velocity of 70 meters per second after 29 seconds of motion. So this problem is actually pretty easy. We're trying to calculate acceleration. Time, of course, is the value that's in seconds, so that's pretty easy to see. Delta V, you might realize, is 70, but even more than that, I think it's important to recognize that we also have two other types of velocity here. We have the initial, like what's our starting velocity? You can see here from rest. Since it starts at a resting position, that's our starting velocity at the beginning. It's a 0 initial velocity, and our final velocity is 70. So we can see that subtraction occurring here as well. This delta V could have been found by taking 70 minus 0, but since we don't really, 70 minus 0 is just 70. So it doesn't seem that groundbreaking. Anyway, we'll just get our value. 70 over 29. And that'll give us an answer of 2.41. We could write meters per second per second. This is more common, meters per second squared. It's just that meters per second is more valuable. So, breaking down this acceleration a little more, like what the heck does this mean? Once again, it means we're gaining 2.41, we're gaining that much velocity every second. So I could do a little chart here to kind of show the numbers. 0 second, 1 second, 2 second, 3 seconds. And what is our velocity at each of those times? Well, 0 seconds into the journey, we have a velocity of 0. It starts at rest. After 1 second, after 1 second, we will have gained 2.41 speed. We will have gained 2.41 meters per second. All right, but what's our speed after 2 seconds? And we just add 2.41 to that. This would be 4.82, methinks. 4.82 meters per second. And after 3 seconds, you know, I don't want to, I could do it in my head, but you know, I could if I wanted to. I'm getting 7.23. Let me double check. 7.23. So we're gaining 2.41 every second. If you calculated this fine, don't worry about this stuff. So this is not part of the answer, that's just my little tangent, which I tend to do. Okay, that's about as basic as the calculations can get. But my answer technically is wrong. I need to put a plus sign because acceleration is a vector. If they told us what direction it was, if it was east, we could say that. All right. One more example here, perhaps more. Yeah, we could do one more example here, and then maybe talk more about the units. All right. So let's see a different case. Let's see a case of something slowing down. Your brakes are used to accelerate your car in the opposite direction. So, I mean, acceleration is just any change in speed. So slowing down also counts as acceleration. And with brakes, you really want them to accelerate at a very high rate. You want to slow down instantly in a very short amount of time. So we're going to look at a drag racing car. So drag racing cars are incredibly fast, incredibly heavy, and they don't want to waste the weight that it would have to have brakes on their car. So they might have secondary brakes. But anyway, they use a giant parachute. So after their race, they release a parachute, it goes behind them, and it slows down their car tremendously. And so we'll take a look at a scenario like that to calculate the acceleration of the drag racer. Here we go. After completing a race, a drag racer deploys a parachute to slow down. After completing a race, a drag racer deploys a parachute to slow down. Their speed decreases from plus 28 meters per second. You know what, that should say velocity, but it's okay. To plus 13 meters per second in a time of 9.0 seconds. calculate the acceleration of the drag racer. You could leave speed if you want. Anyway, I'll read it back. After completing a race, a drag racer deploys a parachute to slow down. Their velocity decreases from 28 meters per second to 13 meters per second in a time of 9.0 seconds. Calculate the acceleration. So here is our original equation. We're trying to get acceleration again. But I'm going to make this equation a little fancier. So remember, we have this over here. This is a property of anything with delta. And I'm going to take this value on the right, I'm going to take this, I'm going to plug it in there. Because they didn't give us delta V. They told us two numbers. So this is just something cool that you could do. I'll probably just give you both forms of this equation. So if I were to give you a quiz, I would probably write the equation in both of these ways, so you can choose whichever one you like. And now we don't need to do any side math. We can plug everything in right now. So here we have it. A equals, let's see, which of these happened first and which of these happened second? Looks like we went from 28, so that's VO, to 13, so 13 is VF. So we'll do 13 minus 28 over 9. So I have -5 here as the answer, divided by 9. And that's -1.67. Meters per second squared. So in this case, the drag racer, since they're slowing down, they're losing 1.67 meters per second squared. And notice that it's negative. Usually the negative means that they're slowing down, but there are some rare cases in which that is not true. So I'll write it exactly as that. This doesn't say in all cases. This is just in many cases. I'd say most cases too. In most cases, negative acceleration means the car or whatever, the object, is slowing down. And there is our 2 examples. Let's see if there's something else we can go over. We'll stop it there. I might make a part 2 of this, but I think that's a good place to stop. Let me know if you have any questions, and I will talk to y'all soon. Cheers.